Thank you. Essentially, you may have missed this morning the workshop that we ran with MatWorks. And essentially, the workshop was detailing for a couple of hours with hands-on this topic. This topic is essentially fundamental in the automotive space. And I would like to mention that that's a research paper that has been accepted at the research track. So first author was my student, Martin. And another key person in this work was Brenda Zhuang from MatWorks. And we had the support of the Martin University supervisor, Professor Facchinetti from Università di Pavia. So on their behalf, I'm going to comment this project. So essentially, why to be interested on that? Because here we are trying to apply fixed function AI in the context of motor control. And why this is quite interesting? Because at the same time, we need to tweak the accuracy. It's not a classification problem, it's a regression problem, but for latency critical system, because here the solution is going to be inserted in the control loop of a permanent magnet synchronous motor. So the challenge is currently quite high, and in the future will be even more challenging. But the way we are commenting this word, the way we developed this project was from a methodology point of view. And so what we proposed at the workshop and in this paper was a methodology based on MatWorks solutions, so Simulink and MATLAB, and their capability to shape, to support the design of the neural network, including a number of optimizations, plus the ST technology, called the core technology deployed on the developer cloud to automate and make efficient mapping on microcontrollers and measures the cost of deploying such type of workload measured directly on a physical microcontroller, a family of microcontrollers. So all these details were in this today workshop. So why it's important, the topic? Because we are focused on automotive. Yeah, currently the electrification is a macro trend, we all know, and especially in Europe, not sure in US, electrification is challenged today. But I'm sure that the progression will have its own trend, and the amount of silicon due to the electrification of the car will increase in the next year, and essentially will be on two dimensions: the battery management system and the traction inverter. So let's go to the traction inverter. In the traction inverter, and in particular in the permanent magnet synchronous motor, you have two essential components: the stator with a lot of windings and the rotor, which is featuring magnetic material. Then attached to the windings, there is the vector control unit. And what are the properties here? Consider that, for example, control vector has to run at 20 kilohertz, which means 50 microseconds in total to close the loop, but the trend is to go to 100 kilohertz, 10 microseconds. Now you start to understand how latency critical is this type of chip, solutions. So definitely, that's a different field from image processing, audio processing. That's not 20 frames per second, 30 frames per second. That's really running at the frequency I was mentioning before. So a little bit of context. We know Maxwell equations. If we, in a winding, let it flow a sinusoidal current, then we have a magnetic field which is oscillating, okay, sinusoidally, okay? And then if we add multiple windings on which sinusoidal current flow, then we generate multiple magnetic field which interact with the rotor, which has its own magnetic field. So essentially we are trying to move, to convert electricity through time-varying magnetic fields into mechanical energy in order to move the car, and vice versa, because it can be inverted, from the mechanical motion generate energy. And here the game is we have typically three phases. So if you let these three magnetic field, three vectors to combine, then you have in three space a magnetic field represented by a combined vector, which is essentially describing the dynamic of the field. Now, the point is that if you sit on the rotor, then the rotor shall rotate. So this is a different reference system composed by two components, the D and Q. Obviously, you want to minimize the D force and you want to maximize the Q force. So how to control this process? Well, you could control directly and only the rotating magnetic field, but this implies that you have to control directly in speed and torque these three phases. While if you apply transformations, typically the well-known Clark and Pack transform, you move from this reference system to the DQ reference system, and then the control gets simplified. But then you need also PIDs. So the PIDs controller essentially are linear controllers, and therefore with the P part you essentially factor the current differences between the reference and the measured speed. With the integrative part you get the history of the history contribution, and with the derivative you try to understand the trend. Now the point is that this can be put in crash in very challenging conditions. So I tell you just, maybe it can sound a joke for you, but if you remember a guy which was called Michael Schumacher driving the Formula One, this guy was using the accelerators as a switch, only released or only touched. So this let me think that maybe the speed reference I can play between two states with the step functions. So I designed two cases. Case one, we have 2 transitions per second in terms of speed with a step function of increased dimension. And in blue, clearly, I put in hard conditions the PID, especially the derivative part. And then you get these overshoots, which is a waste of energy. And you know, any energy coming from the battery management system and to the battery management system has to be saved. These are drops of water that we cannot waste. First case. The second case, 10 transitions per second. Here we have steps and ramps. And the situation is even worse. The PID cannot handle that. You see, continue to oscillate. So how to solve this problem? Methodologically, here comes into the picture the proposition between ourselves and MatWorks. So Simulink is the de facto standard in automotive applications. Every guy that plays algorithm and controls in automotive are familiar with MATLAB and Simulinks. And now with the deep learning toolbox, we can design the neural network and play a number of optimization. But when you design a neural network, you need to be aware that it's deployable in a microcontroller. A microcontroller that can already today run the control loop at very high speed. So for example, at 20 kilohertz, it can close on the stellar E1 the control loop in 10 microseconds. So definitely we need to make sure that is deployable on edge microcontroller automotive grade. So optimization are required. Which type of optimization? Hyperparameter optimization, pruning, quantization maybe. And before to launch huge training steps, we need to make sure that these workloads are deployable. For example, on the stellar microcontroller. To do that, we use the developer cloud. Today we saw the application, you upload the neural network on the developer cloud, you are attached on the backend, essentially in the backend there are attached the physical microcontroller and the deployment is automatic. You get back memory occupancy figure without unwriting any code and execution speed. There is no emulation, just execution on the target. So what is the solution? Essentially, you saw that there are elongations, there are overshoots between the desired answers and the PID. So this generates an error. We would like to essentially remove this error from the response of the PI. So the AI, the neural network, need to generate a compensation factor. Like in sensor calibration, and then subtract this factor from, which is time varying, from the one generated to PID, and hopefully the result is compensated, free from overshoot. Now, we need to prepare a data set. So essentially, we get the behavior from the PI, and we generate an ideal answers, an ideal output, and then we train with such a curve the neural network for case 1. For case 2, the ground truth is generated also through a compensation factor which is exponentially decaying, and then this has been used to create the data set. And today we saw how to generate that through MATLAB. And then a neural network was devised. Essentially, this neural network is similar to a time is a time-varying convolutional neural network, but there is no convolutions. There are dense layers. There are 2 branches plus residual. So at the end, a fully connected layer were good enough. Good enough, how many parameters? 1700. And 2 order of magnitude in terms of ratio between the available samples and the parameter of the network, so that generalization can achieved. And on so what are the performances at the end? On the left, you see huge overshoots on the case 1, which are definitely mitigated by the neural network. So in terms of performances, we have a 10% increase on the case 1 about the max deviation, but in terms of average and max overshoot, there is a clear benefit. The more challenging case, also, this case 2 is evident. There was a decrease less than 2% of the max deviation, average deviation, and 70% in terms of max overshoot. So the neural network is doing its work. And so that's the good direction. Then, thanks to the MatWorks facilities, we can optimize. What does it mean? Well, it is well known that hyperparameter optimization based on Bayesian optimization is the way to go, and it can help really to mitigate the cost. Then projection is quite important, because here in particular the algorithm proposed by MATLAB is through PCA. So essentially we analyze the principal component of the activation, and then we decide which weights need to be removed in the topology, which is quite good, and then quantization. So then obviously all these variants have been deployed on two kinds of microcontroller. For industrial application, this is typically in our proposition the STM32G4. For automotive is the Stellar One. So with integrated flash and memory, and I think the G4 ran at 160 megahertz, the Stellar One E1 at 300 megahertz. So no matter what we did, essentially, in the best case, it was a 70 microsecond inference time. Good enough? No, definitely no. I was saying that without AI, we closed the loop at 10 microsecond on the Stellar E1. So that's a first step. Obviously, hardware acceleration is required, especially in perspective. And therefore, there is still work to do on this respect, which means to develop fast hardware acceleration, very low latency. And this is something to be done in the future. And there are other challenges. People in the motor control expertise wonder why we didn't use model-based predictive control. That's too complex to be embedded. And we need high-level models, maybe to generate data and to train even better the neural networks. And there is still much work to do on the traction control. So I'm done. Any question, please? And there is the paper in Arxiv. If you want to read all the details, just scan this QR code. Thank you.